to my classes on fundamentals of electrical circuits. As before, we have already moved into AC circuits. And today, in this session, we are discussing a few more tougher problems, perhaps. But then, as I said earlier, AC is easy, and so we discuss mostly easy methods. If we go to the first problem itself, it can be seen that it is having two different sources. Okay, and one is a voltage source and other is a current source. Both are sinusoids with maximum value of 20 and 10 respectively. The only difference happens to be that the frequency is different. On the left side source, which is a voltage source, as shown by the tilde, we have an omega equal to 10, whereas the current source has an omega equal to 5. And in between, we are having a capacitor, and it seems as though the capacitance voltage is going to be asked because it's called as VCT. We also have a resistor as also inductor. And two different values are given in A, B, C, D, etc. without units. So let's read the problem. The voltage across the capacitor, as was expected, as shown in the figure, is expressed as VCT is equal to A1 sine omega 1 t minus theta 1 plus A2 sine omega 2 t minus theta 2. The values of A1 and A2 respectively are. So the values that are given as A, B, C, D or the MCQs. The solutions to the MCQs happen to be A1 and A2 respectively. Does the question tell you how to do the problem? I would say it does, because the solution has two components, or in other words, it is going to be what is called as a superposition. Superposition of two aspects. One is when 20 sine 10t was applied, because we have a linear circuit there, and at that time the current source is open circuited, as is applicable to superposition. Then we apply 10 sine 5t. Now omega becomes equal to 5 and the voltage source is short circuited. So it's as simple as that, and again I repeat that it is actually the question which is telling us the route towards the solution. So we apply superposition. We apply 20 sine 10t. At that time the ohmic value or the reactance value becomes 1 by omega into C, or omega is 10 now, so it becomes, and C is equal to 1 farad, so it becomes 1 by 10. Okay, and what happens to the current circuit? It is open, so that particular impedance value need not be, that is the impedance value of 1 Henry need not be considered at all, because we have an open circuit here. So now we have a potential divider, and how does the potential divide itself? It divides in such a manner such that 20 is shared between the case. 20 is shared between the two. And why do we look at 10, 20? Because the solutions have given A1 sine omega 1 t minus theta 1 and A2 sine omega t, which means that the maximum values are applicable. So what is going to be 20 into, of course, 1 by 10 divided by 1 plus 1 by 10. So obviously we are seeing that we are having a very small voltage across the capacitor, okay, and it is near around 2 because 20. Okay, so that's all, that's enough, but you can also calculate. Okay, so let's leave it like that. So of the different answers, 5 and 6.4 can be rejected because it may not come to such a big value at all. Okay, 2.5 and 3.5 also seems unseemly, but we'll go a little further. Now let's apply the current source 10 sine 5t, which means that now omega is equal to 5. Okay, and the voltage source is short circuited. So now we are having a different kind of impedance for the capacitor as well as also for the inductor, but now the inductor matters. Okay. Of course, does it matter? The question is again, okay, does it matter? No, it doesn't matter because the current source will always admit this. So now the current source is going to flow through the 1 Henry inductor, whatever be its impedance, and then it's going to split into two. What are the two components? One is of course the 1 ohm. The other is going to be 1 by omega. Omega is 5 now and C is 1, so 1 by 5. So the splitting is between 1 and 1 by 5. Okay, and then finally you multiply that. Okay, so this is what is going to happen. Okay, and what is VCT? VCT is the same voltage which is applicable across 1 ohm as well. So 1 ohm, and when you 1 ohm, when you parallel with 1 by 5, of course the value becomes even lesser than 5. Okay, so it's lesser than 1 by 5. I suppose you know that when you are having a parallel combination, the total combination becomes less than 1 by 5. Okay, I am talking to you about a quick method of doing the problem rather than solving it conventionally. Okay, so what do we see? So now we see that 10 ohms, 10 ampere with the maximum value flows through a combination of two impedances, of which the total impedance value is going to be less than 1 by 5. Okay, so let's take 1 by 5. Okay, so if we take 1 by 5, 1 by 5 into 10, what is it? It's again near around 2. Okay, of course it's lesser than that, so it's definitely it's near around 2. So of the two options that we have now, A and B, which is proper, we see that A is the best answer. Okay, this is the way that you answer gate examinations. On the other hand, you can make your calculations, but what is intended or what is expected from you is to know the fact that, know some of the concepts that were discussed, like for instance superposition. Then again you are having voltage, and you don't even need to consider current division. So I have written it there, current division. You can simply say that 1 by 5, which is going to be the impedance value of the capacitance, when parallel to 1 ohm, is going to have an impedance value which is less than 1 by 5, which means that a value less than 1 by 5 multiplied by 10 is going to give us a value which is less than 2. Okay, so 1 by 5 into 10, so it's a value less than 1 by 5. When you multiplied by 10 will give you a value less than 2. Okay, so 1.998 may be the solution. You can also go for the rigorous solution, and you can find the answers. Okay, so that's from problem number 1. Let's go to problem number 2. So what do we have here? We see again a voltage source. Omega is given as 1 kilo radians per second, or 1000. Okay, 1000 radians per second. Okay, there are two reactances. One is the inductor, 4 millihenry. So in 4 millihenry will immediately translate to 4 into 10 raised to minus 3 into 10 raised to. Okay, so omega L. So that gives us a reactance value as J4 plus J4. Okay, and the capacitance below, and that is 0.5 millifarad. It's not micro. Micro would have got you either a mu sign or a capital M. Okay, so 0.5 mF or millifarad multiplied by, again, 1 by omega C will give you a value is equal to 1 by omega is 1000. Okay, and then you are having 0.5 into 10 raised to minus 3 on the denominator. Milli and 10 raised to 3 cancel. So 1 by 0.5 gives you a magnitude equal to 2, but it's going to be minus J2 because it's a capacitance. Okay, and then we are having a 2 ohm, which is across which we have the load resistance R. Okay, so what is expected out of is that in the given circuit for maximum power. Okay, maximum power means Thevenin's, to be delivered to RL, its value should be. Okay, what is the value of RL? Okay, there's absolutely nothing to do. We can simply short circuit the voltage source. Okay, and we can parallel with 2 with respect to the overall reactance. So what's the overall reactance? J4 minus J2, which is equal to J2. So when you parallel 2 to do 2J, I hope you remember that the total value is going to be 1 plus J. That is A plus, when A and JA are parallel, it's going to be A by 2 plus J by, plus J A by 2. Okay, so now we are having 1 plus J, which has a reactance of root 2. On the other hand, you can use the normal Thevenin's method. Okay, you can and all possibilities. Okay, so even short circuit and take the ratio of VTH by IN. So there are several possibilities. So which is the easiest method you can always choose. Okay. Okay, moving on to problem number 3. What do we have there? 230 volt, 50 hertz. So what is 230? It's the RMS value. Okay, only if you write 230 sin omega t, it means that 230 is going to be the maximum value. So RMS value is given. Omega is also given as 50 hertz, which means that it's 314. Okay, in the circuit showed. Okay, and we have a capacitance and a impedance which is given by ZL 30 angle 40. Okay, so 30 angle 40 means the resistive component is 30 cos 40 and the reactance component is 30 sin 40. So or in other words, XL is equal to 30 sin 40. Okay, so what is asked out of us is that in the circuit shown in figure, what value of capacitance will cause a unity power factor at the AC source? So how do you get a unity power factor? Only if the two impedances balance out, or the reactance is the same as equal to the inductive reactance is the same as the capacitive reactance. So what's the what is the inductive reactance? 30 sin 40. That's equal to 19.2830 watts, okay, which is now equated to 1 by omega c. You know omega, we have already seen it that for 50 Hertz it's going to be 314. Simply find out the value of C. You will see that it's okay. Even here you can use the approximate values, because 314 into 19 point, and you can simply say that it's equal to 300 into 20, okay, and then you can write it out in terms of the microfarad, okay. So what you get there. Moving on to the fourth problem. Okay, here it looks a little complex. When it looks a little complex, the solution is going to be very easy. Okay, of course, it earns you more marks, and that's the reason why it's put in a very complex manner. Okay, so what all do we have there? We have an AC source. The value is not given, but a 10 ampere emerges from it. 2 amps flows through 1 ohm and XC1. And the rest flows through XC2, and then they join together. So this is an important concept. They join together, and then 200 volt is shown. It's not a source. It could be a voltmeter, and then the combined current of 10 amps, which started off as 10 amps, which ends up as 10 amps, flows through XL and R. Okay, and then it returns to the source. Okay, so what is asked is the total power dissipated in the circuit shown in the figure is 1 kilowatt. So this is the additional information given to us. That is the total power dissipated, which means that the power dissipated in 1 ohm as also in the resistance R is equal to 1 kilowatt. What's the power dissipated in 1 ohm? 2 into 2, that is I square R. So 2 is 4. Okay, so the rest is all dissipated in the resistance R. And the question is, the voltmeter across the load reads 200 volts. Okay, so that's also correctly guessed. The value of XL is what? Okay, so we know the voltage across the R-XL combination, which is 200. We know the current through it, which is equal to 10 amps. So what's the impedance? 200 by 10 is equal to 20. Okay, now we just need to remove resistance. Do we know the resistance? Yes, we know the resistance, because we know I square R. That is, it is 1 kilowatt minus 4 watt, which is taken up by the 1 ohm resistor. The rest is all expended here, and that's equal to I square R. So you do I square R, which is equal to 996, and so division by I square, which is 10 square, gives you the resistance as equal to 9.96 ohms. Okay, so now simply square root of 20 square minus 9.96 square gives you what is called as XL. Okay, so a very simple problem, though it looks a little complex, it's easy to do this particular problem. Okay, so moving on to the fifth problem. What do we have here? We have a voltage source, an AC voltage source. As of course, we are doing AC here, and then IS emerges out of it. One portion goes through the RL combination, the other flows as IC. Okay, so IRL, IC. Okay, so IS is equal to vectorially IRL plus IC. Okay, and what is asked? Okay, data is also given. Vs is equal to 1 angle 0. Okay, so the combination, the entire voltage across both the capacitor as also the RL combination, it happens to be 1 angle 0. Is is equal to root 2 angle pi by 4. So what is pi by 4? 45 degrees. Okay, so that tells you something. That is the current is having an angle of 45 degrees. Why? Okay, so let's see that. IRL is equal to root 2 angle minus pi by 4. This is very important, because IRL is the current through the inductive the resistor and the inductive reactance. So what does it mean? That the resistance and the inductance are equal. Otherwise, you wouldn't get a, of course, because it's an inductance, the current is lagging. That's why minus. Okay, and why pi by 4? Because both the resistance and the reactance have equal values. So R is equal to omega L. Okay, so of course you don't know omega, but let's still go further. We know IRL, and we know what is called as the voltage across it. So we know IRL, and we also know the voltage across it, which is equal to 1 angle 0. So what is the impedance? Voltage divided by current. Okay, so when you divide the voltage by the current, you get the impedance. Okay, so what's it? 1 divided by root 2. Okay, 1 divided by root 2 is equal to 1 divided by root 2, which is equal to 1 by root 2. Okay, so this is the impedance value. Okay, and the resistance and the reactances are equal. So now it's going to be easy, but let's just move on to what is required out of us. The first question requires that you get the power dissipated in the resistor R. So you just need to know the resistance value. You already know the current. What's the current value? It's equal to root 2. So root 2 square, that is 2 multiplied by the resistance value. So how do you get the resistance? You know that R square plus omega L whole square, okay, take its square root, is the same as equal to 1 by root 2. And R square and omega L square happen to be the same, or square root of R square plus R square, or 2R square, or R root 2 is the same as equal to 1 by root 2. Okay, so what is R? It's equal to half. L is omega L is also equal to is also equal to half, or it's, or the impedance value or reactance is equal to J 1 by 2. Okay, so I square R is now going to be root 2 square, that is 2 into half, that's equal to 1 watt. Okay, very simply you can do it. Only step by step understanding of whatever has been given is important. Okay. And what else is asked is the current IC in the figure above. Okay, so what is the current IC? It is IS minus IR. Okay, so the accompanying figure tells us how IS is drawn, which is with an angle of equal to plus 45 degrees. How IR is drawn, again the same magnitude but with the angle of lag by minus or angle of lag of 45 degrees or minus 45 degrees. And when you want to deduct IR from IS, you reflect it back, and then you can see that now you are going to have a current as given by the diagonal of the square made of these two current components. So what's it going to be? It is going to be root 2 times whatever is given to us. So we have root 2 into root 2 is equal to 2. Okay, and of course it is leading, so we have and it is at 90 degrees because it has to be midway between the reflected current IR and IS, so it is going to have an angle of lead equal to 90 degrees, so it is J2. As it is, we should expect a current through the capacitor which should lead the voltage across it, which is 1 angle 0 by 90 degrees. Okay, so most of the problem you can do by intuition, the rest you can do by calculation. Okay, so moving on to the sixth problem here. Okay, so here we see a star delta circuit, but the most important point observation that must come to your mind is, this is the reason why I say that always look at the figure first. Okay, so now we see that it's a single phase source. Okay, the source is single phase, it's just that the load is connected in a pattern with which we are familiar in the star delta sense. Okay, so it's not star delta. What is it? It is one element in parallel with two elements in series. So this is the understanding that we need to have. Okay, so what all do we have? We have we have the voltage, we have the current, and we have three equal resistors. Okay, seemingly connected in delta, but it's actually R and R in parallel. Okay, in series, again in parallel with the single R. Okay, similarly we are having a capacitance which of course now we can convert to delta, such that we can look at it in a similar manner. Okay, so what is the other data given? The circuit shown, if Vt is equal to 2 sine 1000 t volts. Okay, so omega is 1000 and 2 is the maximum value. R is equal to 1 kilo ohm and C is equal to 1 microfarad. We also know omega. So what is omega? Omega is equal to 1000 and the C is 1 microfarad. So you can calculate the reactance. Then the steady state current IT in milliamps is what? Okay, so we can just simply start off with two currents being drawn from Vt. One is by virtue of the resistors, and how are the resistors connected? It is R parallel to R, so it is going to be 2 by 3. R 2 by 3, of course 2 by 3 and 1 R is equal to 1 kilo ohm, so it's going to be 2 by 3 kilo ohms. Okay, and current due to this is voltage divided by resistance, that's giving us the voltage is 2, so 2 divided by 2 by 3 is going to give us 3 sine 1000 t. It doesn't make any difference with respect to any angle of lag, etc. Okay, so what do we have here? So of the 4 answers given, immediately we log on to the answer C, because it is telling us there is a component which is called as 3 sine 1000 t. There is no angular change, there is no sine does not go to cosine because it's all resistor. Okay, so the other, let's just test if the other component is also true. Okay, now let's look at the capacitance. Okay, so how do you find the effective capacitance? Okay, so each of these capacitors, since they are connected in star, the delta quantity, unlike in the case of resistors and impedances, becomes C by 3. Okay, and this C by 3 is now parallel to another C by 3 and C by 3 in series, which is equal to C by 3 by 2. That's just like we do resistors. Okay, so we have C by 6. So C by 3 parallel to C by 6. You can add them together because they are parallel, and you get this equal to C by 2. Okay, so now this is the current which is this is the impedance which is drawing current. Okay, so of course you have omega, which is equal to 1000, and C value is 1 microfarad. So put them all together. So we have what is called as J2K as the capacitance, okay, capacitance reactance, okay. So immediately we see that when you divide to sine 1000t by this impedance value, there is a change in angle, there is a change because of J, there is an angle of lead of 90 degrees. So we are having so the answer is going to cosine, and 2 cancel. So we are having the other component as was predicted being the same as equal to cos 1000t. I hope this is clear. The most important point is that this is a single phase. Second is of course the fact that the structure now is not star delta or anything like that, but you can convert from delta component to star just based on the fact that it has 3 extreme terminals. Okay, it's a star connection only for the capacitor, since you are splitting the whole thing. Okay, so now you can go for delta, and when you take the delta of the capacitors, okay, so you can either think in terms of 1 by C. Okay, or you should think in terms of capacitance, in which case the what you use is C into C divided by C plus C also, or you are having C by 3. Okay, and then C by 3 is in parallel to the other 2 combinations which are in series. You have C by 3 parallel to C by 6. Okay, so you get C by 2. Okay, so and how do you find the impedance? 1 by minus J by omega C. Okay, so you get the impedance and then find out the value of the current. Okay, so very simple. I think it is very simple. So moving on to some slightly difficult problem. Here we are having we are having 2 boxes. In the first box we have 10 volts. Okay, AC source. That is called a circuit A, and there is a 2 ohm resistor there. On the other part we are having 3 volt. Okay, as an AC source again, minus J1 as the impedance connected across it. So actually this impedance is irrelevant because it's connected across a voltage source. Okay, let's see if it applies. And then there's an unknown resistor R. Okay, and this comprises circuit B. And what is R? Okay, of course different values are there. All are ohmic values. So it should be asking for the unknown resistance R. Assuming both the voltage sources are in phase. Okay, that's a very interesting concept, because when they are both in phase, then you can actually find out the total voltage across 2 ohms and R. It's going to be 10 minus 3, as simple as that. Okay, are in phase, the value of R for which maximum power is transferred from circuit A to circuit B. So maximum power to transfer from circuit A to circuit B, we realize that the whole circuit in B should be equal to 2 ohms, because that's the way that we are having Thevenin's impedance. Okay, so or in other words, we see that the maximum power that can be transferred from circuit A is the same as equal to V square by 4R. Okay, V square is 10 square divided by 4 into 2, that's 4 into 2, that's giving us 12.5 hours. So this is one part of the problem. Next is of course, okay, this is delivered, so what is taken? Okay, so that you have to equate. Okay, so again it's actually the problem which is suggesting us the answer. So this is delivered, so what does it take on? So how do you find out what the power is that is being taken by B? So of course there is a voltage current relationship. Like for instance, the current that's being taken is equal to 7, as was said earlier. 10 minus 3 is 7. 7 divided by 2 plus R is going to be the current that is flowing. Okay, and what all is consumed power? One is of course the resistor. So it is going to be 7 divided by 2 plus R into R. That's going to be the voltage across the resistor. Okay, so voltage into current is what we are going to see to find out the total power. Okay, the next component is 3 volt itself. 3 volt also draws this current, which is equal to 7 divided by 2 plus R. Okay, so we are having 7 divided by 2 plus R into R as the voltage across the resistor, and the voltage across the capacitor, or this is equal to 3 volt. Okay, so both these voltages are going to be multiplied by 7 by 2 plus R. Okay, so and then equate them, because power given is what is power taken. Okay, so once you equate them, you can solve for R and it becomes the same as equal to 0.8. Okay, this you have to do on your own, because this is actually a problem based on intuition. Okay, there might be other methods, but this seems to be the best method to understand as also do the problem. Okay, so moving on to the 8th problem, what do we have there? So I agree that all these problems are a little tough. Okay? Of course, it's the last of the AC sessions, AC circuits or sessions that I'm trying to help you with. And in this case, we have taken the best of the problems and the most tough, but I think I'm suggesting the easiest methods. Okay, so in the 8th problem, what do we have? We have sin omega t, so value is equal to 1 or magnitude is equal to 1. There is a resistor and there is a string of capacitors. Okay, and Yt is shown across one of the capacitors, but since all the capacitors have the same value, both the upper and the lower capacitors will have the voltage. If it's voltage, it's equal to Yt. Okay. So what is asked is the steady state output of the circuit shown in the figure is given by Yt. Okay. So output should be voltage. Okay. Is given by Yt is equal to A omega. Of course, it depends upon the omega value of the source multiplied by sin omega t plus phi omega. Again, the phase angle will also depend upon omega. Okay. The amplitude A omega equal to 0.25. Okay, A omega is also given as equal to 0.25. Then what is the frequency omega? This is what is asked. Okay, so how do you proceed? Okay, so we know that A omega is equal to 0.25. The same current flows through the lower capacitor also, or Yt is the same voltage which is applicable across the other capacitor also. So in total, the total voltage across the entire circuit is going to be A omega plus A omega, or 0.25 plus 0.25, which is equal to 0.5. So this capacitor also has 0.5. Okay, and now we have a resistor, and this resistor is sharing the rest of the voltage. What is the applied voltage? Which is equal to 1, because it is 1 sin omega t. So 1 minus 1 square minus 0.5. Why 0.5? 0.25 plus 0.25 is equal to 0.5. So 1 minus 0.25 or 0.5 square is going to give us the voltage across resistor. This is obviously the same as equal to 0.5 into root 3. I suppose this is clear. Okay, if this is clear, now we can move on to the rest. Okay, so what do we have here now? We now need to explain that the current through the resistor, okay, which is the same as equal to the current which is flowing through the capacitor assembly. So what's the current through the resistor R? It is the voltage divided by R. So 0.5 root 3, as we computed right now, divided by R is equal to the current which is flowing through the combination. Okay, so what is the total voltage across the combination? It is 0.5. And what is the total impedance? It is equal to 1 by omega C effective. Okay, what is omega C effective? We are having two capacitors in series. What does it mean? It is equal to C by 2. And then another C in parallel. What does it mean? 1 plus half C, or 1.5 C. So we have now 0.5 root 3 by R is the same as equal to the 0.5 voltage across it divided by the impedance, which is 1 by omega 1.5 C. Okay, and then the frequency omega is asked. Okay, I forgot to read it, the frequency omega. So that now we have to just separate out omega. All the other things can be taken to the other side. So it's obviously the same as equal to 2. Why 2? Because we are having 1.5 when it comes to the denominator. We can multiply both the numerator and the denominator by 2. So it's 3. Such that root 3 and 3 together gives you a root 3 on the denominator. So 2 by root 3 obviously comes out. Okay. And then we are having R on the denominator, and C also comes there. So root 2 divided by root 3 RC is very easily the solution. Okay. Moving on to the 9th problem. In the following circuit. Okay, of course, the circuit, it's a simple circuit. There's a voltage source and through the diode. Okay. Through one diode or the other. When the left side is positive, it's the upper capacitor which gets charged, and when it becomes negative, the lower capacitor becomes charged, and there's a resistor there. In the following circuit, the input voltage V in is 100 sin pi t. For 100 pi, RC is equal to 50, the average voltage across the. Okay, there are different ways of doing this problem, but the easiest method is the fact that we realize that we are having omega. Okay, omega is 100 pi. Omega is equal to 100 pi is the same as 50 by RC. Okay, so RC is generally the time constant, and 50 times the time constant is what is shown here. Or in other words, the voltage settles. The voltage across both the capacitors settle together to 100 plus 100. 200 volts. Okay, so in that sense it is 200 volts. On the other hand, if 100 pi RC is very small, then we would have had to compute how much of voltage is getting discharged to the resistor, and then we'll have to the problem would have been different. Okay, so to the last of the problems. Okay, again it looks okay, it's the last of the slides in the circuit in this session. So what do we have here? We have V1 30 angle 45 on one side, V2 30 angle minus 45 on the other side. So it must be easy. Then we have Z1, Z2 and ZL, and IL is supposed to flow through ZL. Okay? An electrical network is fed by two AC sources as shown in figure. Given that Z1 is equal to 1 minus J ohms. Okay, that's good. Z2 is equal to 1 plus J ohm. Okay, so if Z1 and Z2 are going to come in series, then it's going to be 1 minus J plus 1 plus J is equal to 2. Okay, so that may be good. Okay, and Z is equal to 1 plus J. Okay, so that's 1 plus J 0, which means that it's pure resistor equal to 1. Okay, obtain the Thevenin's equivalent circuit. Thevenin's voltage and impedance across terminals XY. So you are going to open circuit XY terminals. Obviously, Z1 and Z2 are going to come in series. Okay, across X and Y, and determine the current IL through the load ZL. Okay, so we are going to find out the Thevenin's voltage. Okay, first. Okay, so with XY open, okay, we realize that we are now having a circuit for circulation of current. Okay, a circuit in which a current circulates. And what is that? What is the voltage which prompts this current? Which is equal to 30 angle 45 minus 30 minus 30 angle minus 45. Okay, so that's what is shown in the diagram, which we have something akin to what we did earlier. So we see that it's the same as equal to, of course, as we saw before, there's 30 obviously, and then there's a root 2 multiplication because of the resultant being on the diagonal of a square, the square having the same sides as also 90 degrees between them because of 45 being reflected back. So we are having 30 into root 2 angle 90. Okay, as was done in the earlier problem. So I'm not going to dwell deeper upon it. Okay, so what is the current? Okay, so why do we need the current? Such that we can find out the Thevenin's voltage. Okay, so what's the current through Z1 and Z2? Just divide by the impedance. And what's the impedance? 1 minus J plus 1 plus J, which is equal to 2. Okay, so we are having 15 root 2 angle 90, or J 15 root 2 as the current flow. Okay, and this creates a drop across Z1. Okay, you can calculate this from any side to get Thevenin's voltage. You have to look to only one side. So we are looking leftward from XY, and we see that 30 angle 45 minus J 15 root 2 into Z1. And what is Z1? Z1 is the same as equal to 1 minus J, which is the same as equal to root 2, 1 square plus 1 square root 2 and minus 45. Okay, so root 2 minus 45. Okay, so we see that 30 angle 45 minus J root 2 into root 2 angle minus 45. So what is 15 into root 2 into root 2? It's going to be 30. Okay, and what is J? J is angle 90. Okay, angle 90 and angle minus 45. It's going to be angle 45. Okay, so 30 angle 45 minus 30 angle 45 is going to be 0. Thevenin's voltage is 0. Okay, it looks complex, but the Thevenin's voltage is 0. Okay? So it's very interesting that now Thevenin's voltage is equal to 0. Okay, so if you look at the Thevenin's impedance, we have 1 plus J and 1 minus J in parallel, as was mentioned before. If A plus J and A minus J, sorry, A plus JA and A minus JA are in parallel, it's the same as equal to, okay, it is the same as equal to A square plus B square by 2A, which is equal to 1 ohm. Okay, so Thevenin's impedance is very easily obtained as equal to 1 ohm. And okay, what else is asked is the current through ZL, which is, of course, when you're looking at Thevenin's voltage being 0, the current is going to be 0. Okay, so that's as simple as that. So mostly all the concepts that we had earlier talked about were revisited. Moreover, it was shown that both the maximum value for a sinusoid as also the omega are going to be important, and accordingly you have various versions of the problem wherein the omega becomes a matter of important of concern. Okay, so thank you.